Bismillahirrahmanirrahim. Greetings. This is going to be the 5th lecture in a series of lectures designed to build the path toward the fundamental theorem of calculus. Now, since repetition is a good process of learning in a sense, so let me go some of the highlight of the previous lectures before we start today's lecture officially. Now, in differential calculus, we are given a differentiable function, a function which is smooth, and when you say differentiable, usually means smooth and continuous. And then from that, we apply the definition of derivative and come out with an explicit function f prime of x, which is derivative of that. And that process usually is not too difficult. And the definition of derivative, as I have already mentioned also, can be considered as a theorem. And deductively, as a matter of fact, it can be proved. But anyhow, in calculus textbooks, they call it a definition of derivative. Now, in integral calculus, the derivative of a function is given to us, f prime of x is given to us, and using that derivative, using f prime of x, we would like to possibly find the original function, f of x. You follow, you see the difference between them? And the integration process is a little bit more difficult than differentiation. And when I say possibly, because there are cases that we cannot find the f of x, the original function, and we have to use numerical method as a approximation. And the area under the derivative can give us so much information that we can know the outcome of the f of x that we don't know about it to any accuracy we want, any accuracy desired, without knowing f of x. That's fantastic, is it not? Okay, now, in the previous lectures, we used the slope of tangent line as a diagram and a graphical illustration, and we came out to the conjecture that the area under the graph of the derivative can give us information about the function that the mother function, the original function, f of x. Sometimes it can give all of it, sometimes it can give the approximation of that. Now, in this lecture, we are going to use some familiar examples to further enhance our conjecture, and then if we are kind of convinced, then we can go through the Riemann sum they call, and that can lead us to the theorem, which means deductively this concept can be proven. That's what Fundamental Theorem of Calculus is all about. Okay, then let's get started for today's lecture. Now, I have already written some terms that I'm going to put it on the board and then stay out of way, and the rest of them I'm going to lecture being stay out of way and putting on the board in a sense. Now, these review terms, I am not going to go over them. I just put them on pause for a few seconds. You can pause your computer and take a notes if you wish. And some of them maybe you are already familiar and you can just bypass it. Okay, then let me put this one on. Go ahead and zoom it if I may. Okay. Okay, I suppose that is enough. So let me now go for the next one. Okay, let me now zoom back. That's good, that's readable. Okay, let me go over them if I may. Now here, you know, we are familiar with velocity and distance and acceleration. Suppose a car is going with the velocity of, let's say, 50 miles per hour. So this is its velocity graph, is that right? Now, velocity times time is the distance, is that right? So the height of this graph is what? Is velocity, which is constant. Means acceleration is zero. You have put the cruise on, the velocity does not change, but naturally the distance is changing because velocity is positive. The distance is increasing. Now, here, velocity times time, as we all know, is the distance, is that right? So that means the height of that is velocity, the width of that is time, that means the area under this graph should really be what? Should really represent the distance. Which means is the mother graph, is the graph that its derivative is that. And that is exactly the case, because the derivative of distance is velocity, the rate of change of distance. Now, let me go to this one that I just mentioned, if I may. Now, here, this is the velocity, the derivative function, all right? And that is what the height of that is 50. The width of that is what? Is t. You can select any numbers you want. For example, if you select 3, means you have covered 50 times 3, 150, let's say, miles. So the area under this velocity graph, under this f prime of x, f prime of t in that case, represent what? Represent the mother function. In this case, is the distance. Now look what happens. 50t, you can also consider that as to be this function, which is what? Which is a linear. That is the graph of f of x, f of t equals to 50t. Now, this one, as I have written already, this is the linear representation of the original function, and the area was the area representation of the original function. Sometimes I call this one a skinny representation of the function, and area under the graph, I call it fat representation of the function. So they both give the same outline. For example, if I give here 3, he gave me 3 times 50, which is 150. If I give also 3 here, he gave me 3 times 50, 150. The only difference is that here I give it 3, he gave me my single point here, which is on the graph of that. When here I give 3, I have to go to the left end point of the interval, in this case is 0, and add all those areas up to and including to 3. So the entire area from the most left, A, 0 in this case, to 3 will be what? Will be my f of x. Do you follow me? Okay, now let me go to next one. So the next example is now in the next example, the derivative function is not constant, as you can see. The derivative of a function that I selected is 2t. As you see, as far as the velocity and distance is concerned, the velocity is increasing. You can see that for yourself. Huh? So if the velocity is increasing for each time, that means that the graph of the original function cannot be linear. For each interval of time, the velocity is increasing, is bigger than previous one. So we want now to see the area under this and the representation of that as a skinny. So let me go to the next one. So again, this is what? This is the graph of a derivative of a function. So we are seeking to find that function, all right? So let me cover this part for the time being so that we can concentrate on this one first. Okay, here, this is my f prime of x, 2x, all right? And then look what happens. The area of this geometrical figure, which is a right triangle, is what? Is 1/2 height times base. So, for instance, if I give 5, the height of that will be what? Will be 10. So that means the height of this right triangle is 10. The base of that is 5. 10 times 5 is 50. And according to the formula of area of a triangle, 1/2 height times base, half at 50 is 25. So the area under this graph will be 25. When I give him 5 to this as an input, he gives me 25 as an output with the area. You follow me so far? Now, look what happens here when I go to the skinny representation of that function. Okay, let's see now what happens to that. Now here, this is the graph of f of x equal to x squared that we already know about. As I said, we can learn from the examples that we are familiar with to infer, to learn, to understand the concept of something that we are not familiar yet. So this is the graph of that. Look what happened. If I give him 5 to this graph, f of x equal to x squared, he gave me 25. You see that? So he gave the output of that is same as the output of the area under the derivative function. So that makes my conjecture kind of stronger, that the area under the graph of the derivative is the original function in a sense. You with me so far? Okay, now I put both of them in one diagram just for the, let me put this one around. Sorry for my primitive equipment. Unless inshallah soon I get a good teaching position somewhere and I have access to better equipment. All right, now let me demonstrate this one in the same graph. Okay, here I put the mother graph f of x equal to x squared and the area under the derivative on the same so that we can see. And here I wrote that f of x equal to x squared and a of x to be the area. Then I said they are equal. So here, 1/2 height times base, he give me the area of this triangle, and then the output of that area will be same as if I give the input for what? For the let's say curve function, or skinny I call it, or 1D function. Do you follow me? Now, for instance, here if I give him 5, as I already go over that, this graph, this one gives me 10. Because what? Because f prime of x is 2x. 2 times 5 is 10. So the height of this triangle is 10. The base of that is 5. 10 times 5 is 50. Half of the 50 is 25. So the output of this one is be 25. As I have already mentioned, I'm just repeating. And then when I give him 5 to this, the original function that I already know about, then what does it give me? It gives me again exactly same thing, 25. So I can see very good relation. So it looks like I have enhanced my conjecture to come and go possibly for the proof. Now, I have the last one. I would like to put it here. Then I go and zoom back and say a few more words and close today's lecture. Now, let me see what this one is saying. Now it says that f of x is the original function having f prime of x as its derivative, right? Now, a of x is what is the area under the graph of f prime of x, all right? Now, knowing f of x, we can accurately determine the area under the graph of the derivative. And they call it what? Definite integral. Very fascinating. Which means we can determine the area under the graph of f prime of x precisely no matter how the curve of the derivative looks like. It's fascinating, is it not? Now, here, not knowing f of x, we do not know f of x, we can use a of x, which is the area under the graph of the derivative, to approximate f of x to any desired accuracy, as I've already mentioned. All right, then, let me zoom this one back and say a few more words, and that will be for today's lecture. Okay, then, it's a very fascinating subject. Please, if you have not seen them before, I keep repeating that, do not get discouraged. The subject is very, very simple once you get what's going on, and very sweet. And don't forget that this stuff has taken centuries, and gifted mathematicians, sometimes physicists, have worked on that. So it's not that for us, we learned it within 5-10 minutes. That, you know, big the intellectual mathematician like Leibniz spending maybe 10 years for coming for the Fundamental Theorem of Calculus. That is, bridges the gap between differential and integral calculus. Okay, then, hopefully I get the opportunity to upload the entire series, and then I go to some selected topics that I know students have some difficulty from my experience of teaching, and I hope that my videos are beneficial to you. And in the close, I always request for the audience, if they see any error or if they have any suggestion, please share it with me in the comment section below. You will be doing me a great favor. Okay, then I thank you all for watching. I wish you all prosperity and good health, and please stay and remain in good health. So long.